All right, let's go. Basics of software engineering. Software failure occurs because of increasing demands and low expectations. It was first proposed in 1968 because of the difficulty of the individual solving problems on their own. Now this is something which I'm just kind of introducing to you now, and the good thing about this particular topic is that this isn't just about computers anymore. This is about management, project management, and it's about, you know, trying to work out, you know, how you can, you know, work in teams. And it starts to, you know, it's part of the simulacra principle, like I like to say, which is this hyper reality, like the Web 3.0. And if you look at some of the people that sort of lead software projects, you can kind of get an understanding of the kind of people we're looking at. So, for instance, we've got this guy, and this guy is Jens Ostergaard, and he's giving a talk on Scrum. And so he's the sort of guy, you're going to be quite tall, you're going to be a little bit fat. Another guy is Notch, who invented Minecraft. I like to think of Notch as kind of the alpha, and guys like this are kind of still are alpha actually. It's you know, without direct knowledge of what's actually going on inside these organisations, it's quite hard to tell. But this guy's probably is if he's not alpha, he's certainly, you know, a high level beta male. So that's, you know, so these are the kind of people that are, you know, organising these things, and because it's to do with computers, you have to understand that, you know, the whole field of computer science is very influenced by the fact that there's so many more men in it than women, and even though women were kind of the programmers, you can't you know, you have to include these things even when you do all the stuff to do with it and how projects are made. You know, for instance, one guy on his own wrote an operating system which would break all the rules that I'm going to teach you now. So, you know, understand this is how it works within the organization. People have thought about it for, you know, for 40 years. But then again, you also need to think about, you know, the way that sales and advertising have worked. For instance, when I worked in a store, you know, we were taught, you know, I had to sell healthcare to people. We were taught, you know, if it's a slow store, give them a more personable approach. If it's a fast store, you know, you can be much quicker. You can go, hi there, sir, hi there, sir, hi there, sir. So you have to understand there's different requirements, just as there are in sales and advertising and things of that nature. So with that in mind, let's move on. And another point I would like to make is this is going to lead us to talking about UML, which is a very important language, which kind of aims to simplify development of Java, and it's a way, and I quite like it because it's more top down, it's more interesting, it's more to do with the flow charts, and, you know, and arrows pointing everywhere, and there's sequence diagrams, there's all sorts of things which we will move on to later on. Obviously I'll have to actually go through Java first though, so it probably will be quite a bit later on there. So, okay, there's four main activities in all software engineering. We've got specification, development, validation, and evolution. So specification is the initial kind of stuff, then you've got the development process, validate, we check everything's okay, and then we move on to, you know, next one, you know, Web 3.0, Web 4.0. Yep, and Web 4.0 is actually going to involve holograms, interestingly enough. Anyway, so the diversity of products in machines. So there's a lot of, you know, I've talked about this a little bit in some of the previous lessons. However, in this unit, really, you have to really be much more all-encompassing, and it's almost like it's the link between, you know, the computer world and the engineering world. So some of these, I mean, well, actually anything one is actually going to be more than just computers. But they've got standalone apps. You know, that's one kind of thing you do, like Photoshop, 3ds Max, Maya, all that. Then you've got transaction-based, so it could be e-commerce or social networks. Many of these things, they operate sort of these microtransaction stuff, don't they now? We've got embedded systems, which provide functionality to all kinds of machine. Yep, so you get lots of those. There's phones, you know, internal workings of phones. Then you've got batch processing, which is phone payments, which is kind of, you know, another sort of end of the scale there, opposite, I suppose, from the last one. Salary payment, just batch processing. Batch processing is actually a very important concept in computer science. Entertainment systems, that could be games, etc., you know, GUIs and all that stuff. Systems for modeling and simulation, scientific modeling, heavily intensive parallel processing, and that's going to be talked later in the MIPS stuff. Yeah, so scientific modelling often takes you have to work out a whole range of very complex calculations. You might have to spread it over a number of distributed systems. So you're gonna really want to they're very heavily intensive, and to be honest, this unless you're really into that sort of stuff, that's not that useful to know really. Data collection systems, polling and robots. Yeah, so if you're doing like robotics and stuff like that, when, for instance, when you're trying to work out how far away the robot is from the wall or something, you might want to fire a light back and forth, and then measure, do a simple calculation to measure how far away it is, and then do that, say like however many times a second, and so that's that. System of systems, it's composed of a number of systems, so that's kind of so multiple systems working, and to be honest, I suppose that's kind of the real McCoy stuff, And you also think about ethics, and this is obviously something which in computer science doesn't really make much sense really, because you don't really think about ethics. So it's kind of strange that I think other fields will have to probably deal with this more rather than this subject. I think to be honest, I mean, for me personally, I find it very important to think about ethics. So, but then again, it's a difficult subject. So, but they're the main things: confidentiality, competence, IP rights, and computer misuse. So there's no point going in saying, I'm a brilliant programmer when you're crap. That's the main point, I think, really. Competence. Okay, so this is the waterfall model, and this is actually the best model. So I'm saying that that's purely personal statement, but I'm pretty sure it is, to be honest, because it was the first one that got invented, so it's the best. Often once people start thinking about things, they overanalyze it, and then it gets worse. And unfortunately, that's what's going to happen here. Hopefully, the actual quality of me talking won't get worse, but I'm sure it won't. I mean, how could it? Okay, so it's a plan-driven process, the waterfall model. So yeah, we have to make a nice plan for it, and that's that. So requirements analysis and definition, so work out what we need, define it. System of software design, it kind of looks a bit like what we talked about before, doesn't it? System of software design, then we have implementation and unit testing. Unit testing is very important. It's a way to check for errors in your code. A lot of universities will check, will run the tests. You have to run a test for the class and stuff like that. You'll need to run a test and see that everything's working, see your code's not broken. And then we have integration and system testing. So we integrate into the system, and then we do everything, we do it. That's basically deployment, I suppose. And then after that, it's operation and maintenance. And that's obviously the longest part of the process, because you have to actually make sure that it keeps on going. And that's pretty standard. So there's also incremental development, which is this is incremental. So there's very important functions in there. You've got I++, and that just does a loop, doesn't it? And it goes up by 1 each time, goes around a loop and out by 1. And that's basically the same sort of concept that we're talking about here. Incrementing slowly, gathering together, getting more and more and more and more and more and more. So that reduces the cost of accommodating changing customer requirements. It's easier to get customer feedback, rapid deployment of useful software to the customer. So yeah, you can literally go out with the bare bones, and then you get more and more, and it becomes fully fleshed out. And you got all that time, I suppose, to get all the feedback and everything. So that's good. However, there are a lot of existing bureaucratic procedures, organisations. So that can actually be a bit of a problem. So it's not a visible process. So if obviously most computer science don't really want to be working with these managers, and it probably won't be like that in the future, in the very near future actually. Because it all depends really on the social skills that people in computer science develop, and you can't really stress that enough. If you haven't got social skills, unless you're, it depends what you're going for. In general, there's a small percentage of people who are incredibly elite and who want to really develop things forward. I was watching a Lisp lecture, and I could tell that some of the people in the audience there, they were really had real antisocial problems, but they were probably like some of the best people in the whole world. So it depends how you want to look at it, really. But yeah, I mean, in terms of this, you know, it's like it's not a visible process. Managers cannot see regular deliverables. So yeah, you know, don't even bother going to managers, because you know you can't, because you've got nothing to show them really, because it's all like a mess and they wouldn't understand what anyway. So, and there's new increments added, overall system structure degrades. So yeah, so often once you get it, you get a very bloated system. You start being exploits that people can just jump in with their JavaScript or their SQL stuff, and they can just fuck it all up. Okay. Then we've got reuse software engineering. I'm not really going to go into much more detail. That kind of should be obvious, you know, that if you go to like a website like Stack Overflow, yeah, Stack Overflow is called this, Stack Overflow. If you go there, you'll you might be able to find something about it there. It's just, you know, actually, well, it's not even that. It's like that is how you do it. Yeah. Okay. System design. Okay. Architectural design. Overall structure, subsystem, and components. Interface design. Looking at the interface between system components. So yeah, this is just, you know, this is literally the basics of system design here. So yeah, architectural. So that's overall structure, you know, and then the subsystem, and then what components you actually need to, for the system. Interface is going to look at the interface between the system components. Remember, like in the last lesson, when we talked about networking, you know, you can imagine, like, I mean, we'll be talking about like the interface between, say, TCP on one machine and TCP on another machine. They're the sort. I mean, that's sort of like a parallel that we can draw here. Okay, we've got component design. Component design is individual components, how we want to design them and how we want them to operate. And we have database design, very much, you know, what we're going to be using, you know, SQL, Oracle, you know, what we're going to do with the database. Many, you know, everything runs on servers now. So 99.9% stuff's on servers. Okay, and then we're going to talk about rational unified process. This is heavily influenced by UML. I believe it's Universal Markup Language. I believe it is, but you know, correct me if I'm wrong. But I believe it is. And this is like a different way. It's like it's going in at a different angle, I suppose. It like seeks to find the different perspectives of the project. So you might have a dynamic perspective, which would show sort of phases of the model over time, or well, you're going to have all of these actually. This is the whole point. The power is in all of them. So you've got a static perspective, which shows process activities enacted. What processes are we going to be doing in this? You know, and then we've got a practice perspective, shows good practice to be used, and there's like, you know, style guide. So dynamic, static, and practice, they're the things you need. And yeah, we're obviously going to be talking more about this stuff in the future as well. And we're going to move on to this. Remember that guy at the beginning I showed you? If you want to find about Scrum, it's actually a term derived from rugby. You might want to look into that lesson I showed you at the beginning. There's extreme programming, which is very, very popular. These are examples of agile software development, which we'll talk about later as well. But yeah, these, you know, this is like a little snippet into the next section of this. But thanks for watching, and I will see you next time.